Welcome back.
So
During last lecture, we began our part of the course devoted to statistical field theory. And we defined the statistical field theory as a theory, for example, statistical mechanical theory defined by some partition function, for example, a canonical partition function, where the stochastic variables that enters the canonical partition functions are not positions, but are not spin, but typically are fields. So what you need to do is to integrate overall the configuration space, and the configuration space is the value of the fields at any point in space. And you can always think about this as you are actually discretizing space, putting a field variable in each point of space, and then sending the number of field variable to infinity, because that's, after all, just the definition of path integral. And now, as a statistical mechanical theory, this guy will have a partition function with a Hamiltonian, which will depend on my dynamical degrees of freedom. And the dynamical degrees of freedom depend on temperature in the Boltzmann factor, and we can set the temperature to be equal to 1, which basically means that we are measuring the energy in units of kT. So in the rest of these lectures, I often will completely neglect the presence of the temperature. Now, we had a kind of an extensive discussion on when it's beneficial from a statistical mechanical point of view to use field degrees of freedom as opposed to, I don't know, position degrees of freedom or explicit spin degrees of freedom. And our idea is that typically fields are beneficial anytime the average values of these fields varies over very long length scales, so that you can discretize much more coarser graining. You can use a much coarser lattice for fields than you would have if you were to use the atomic lattice or if you were to use individual particles. So that in the end of the day, you save degrees of freedom. There are also other advantages which come from the fact of being able to analytically manipulate field theory, as we shall see today, which come at play. But from a physical perspective, rather than from a mathematical perspective, I would say fields are useful in statistical mechanics when you're interested in soft dynamics. And this is quite interesting because if you think about it, in relativistic quantum mechanics, fields are useful in the opposite regime, where you actually are interested in very high energy dynamics, where you need to combine quantum mechanics and relativistic theory. Okay? The other thing where we said last time is that solving a statistical field theory to all practical purposes can be reduced to the problem of computing any possible two-point function. Any possible correlation function. So solving a statistical field theory is basically equivalent to computing arbitrary endpoint functions. And in here, I would say correlation function. So what is an endpoint correlation function? We defined it last time, is a function of n variables. And it's the thermal expectation value of n product of n fields, each one evaluated in general on a different point. So if I am to write this endpoint correlation function explicitly, I would write this as a path integral with n fields, 1 phi xn, my Hamiltonian, divided by my n, the same quantity without the Hamiltonian, without the fields, which is the partition function. So the statement solving a theory is equivalent to solving this problem follows essentially from the fact that you can tailor expand any observable you want in powers of fields, assuming it's an analytic function of the fields. And normally we're interested in in values of the fields that are small, because maybe we're looking at, because that's where the correlation lengths typically diverge. So if I have an observer, if I can write, say, the quantity that I want to observe as a potentially analytic function of the field, maybe non-local but analytic, then clearly I can write this as a sum over, terms. I will have a sum with maybe a local term. Then I may have a sum over, integral. Then I might have a sum over bilocal terms. And I can go on arbitrarily. This kind of expansion has a name in field theory. It's called operator product expansion. So the possibility of taking any observable and expanding in power of fields. But I will not concentrate on that here. In quantum field theory, this is a well-established techniques for getting non-perturbative physics out of field theory, but it goes far beyond this course and probably far beyond all the courses you will be exposed to in this master. Now, so this means that basically by computing endpoint correlation function, we can compute arbitrary thermal averages. And for reasons that will become clearer later, and perhaps even today, I think you will be convinced soon that by computing correlation function, you'll also be able to compute the Helmholtz free energy, or possibly even the Gibbs free energy by Legendre transformations and so on and so forth. So even state functions follow from endpoint correlation functions. Okay? So once you have thermal averages and state functions, you have everything you want from statistical mechanics. And therefore you solve your field theory. But of course, to solve the field theory, you need to go back and being able to evaluate this integral, which is an infinite dimensional integral, for your specific Hamiltonian of interest. And this is, of course, a formidable problem. Because, as you well know since high school, integrals, even in one dimensions, integrals are not always something you can actually compute analytically. And in general, I would say there are two avenues you can take in order to compute endpoint correlation functions. One avenue is analytic plus approximations. In other words, you try to reduce the problem of computing this to some series, possibly, or anyway, you approximate this problem that you cannot solve with a problem that you can solve. It can be a variational approximation, it can be a perturbative approximation, it can be a saddle point approximation. We're going to define a number of techniques to do that. But that's one way. And the advantage of having analytic approaches plus approximations is that you so the advantage is you retain physical insight at each step of the calculation. The disadvantage is that you, in principle, lose accuracy. I want to emphasize on this because when I had a chance to meet you guys meet the students in person, I spent quite a long time on discussing these issues that are more general in physics than the technical aspects of the course that we are looking at. Physics is all about understanding, not only being able to predict an observable, but also understand why that observable turns out to have specific values. Understanding is a big chunk of physics. Let me give you an example. Suppose now you have a very powerful computer that can solve the hydrogen atom problem to the 10th digit. Okay? With all the interaction you want, Zeeman effect, you put inside everything, you put the complete Hamiltonian and you give it to the computer, and the computer will give you a spectrum. Then you compare to the spectrum, to the experimental spectrum, and you find accuracy. Then, of course, you'll be happy because your theory matches the experiment and you will not have to discard the theory, right? However, you might ask yourself, what have we really learned? You know, if you look at the spectrum of the hydrogen atom, there's quite an amount of structure. There's an overall structure that follows simply from a 1/n² rule, if you remember your introductory course in condensed matter. But then there was also hyperfine structures. Remember the one that you explained. Now, if you have a black box that basically gives you the best possible numerical solution to any desired accuracy, it is just a matter of going to a more powerful computer. Of course, you're doing a great job in comparing your theory with the experiment, but you're not doing such a great job in understanding why experiment has the shape that it has, right? On the other hand, now think about the way actually the hydrogen atom was understood. It was understood as a progressive series of approximation. First, you were dealing with a Coulomb interaction only. And by a strike of luck, admittedly, you were able to reproduce in the limit of pointless protons the 1/n² law and basically get the overall shape of the spectrum. But you were missing the hyperfine structure. And then you would say, okay, let's put additional physical insights inside by introducing more and more and more ingredients. For instance, you introduce the Zeeman, the magnetic interaction, the spin-spin interaction, the spin-orbit coupling, and blah, blah, blah. And then you would treat each of them perturbatively. Now, none of these calculations would be exact. So you might be expecting a small deviation for an experiment. On the other hand, at each step, you have a reasonable fair insight into what is producing what, right? For instance, you would understand that the hyperfine structure of the spectrum is a relativistic effect because they come from spin orbit and Zeeman effects, which involve magnetic fields. Okay. So the analytic approach has advantages and disadvantages, and so does the computational approach. The computational approach is exactly complementary. You lose physical insight. But you gain accuracy. So there is no better or worse. There is no better or worse battle between analytic calculations and computational approach. In a healthy scientific field, you need both because they provide complementary information. So what is the in the following days we're gonna discuss both analytic and computational approaches to field theory, so that you will be equipped with say a background that will enable you to understand the basic literature in both directions. Okay, so last lecture we began discussing some analytic approach, and the first thing we notice concerning analytic approach, so analytic and approximate, is that you've got to start somewhere. Well, even before there, the first thing we notice is that there is a compact way of representing all the physical content of a theory, which corresponds to writing and possibly computing the generating functional, which is the partition function of my theory with an additional linear coupling to an external arbitrary field J. So let me write it this way. H is the Hamiltonian of my theory, which I will assume will not depend on linear coupling. Well, you might have a linear coupling with a magnetic field, in which case J becomes the magnetic field. But in general, you might have a theory that doesn't have any linear coupling to an external field. But if it doesn't, then you put it inside by hand. So this may be unphysical. However, even if it is unphysical, even when it is unphysical, then we might it does retain a great utility. In fact, typically endpoint correlation functions can be obtained by taking n times the functional derivatives with respect to the external sources. The negative sign comes from a negative sign here. And of my generating functional, then you're going to divide by the generating functional and eventually set the source to 0. So if you can evaluate the generating functional, then of course you have evaluated the field theory. Now there are a number, not only one, but we will discuss one, of analytic approaches which are based on the fact that in certain cases you can actually evaluate the generating functional. So evaluating Z of J is possible, and we're gonna show this in the most well-known case is that in which in case the Hamiltonian is a quadratic function of the field. The the notion and this fact will ultimately lead to what is known as perturbation theory and Feynman diagram, which we will discuss in the next lectures. But in passing, I'd like also to mention, without going into detail, that this concept of generating functional is also useful when you want to devise rigorous low energy effective field theories. So in other words, you have a field theory defined by a generating functional, and then you write the same generating functional in terms of effective fields that describe the low energy dynamics, and then you equate the two generating functionals. So this is outside the statistical field theory course, but say, just to be more specific, I jump ahead and I talk about QCD for a moment, quantum chromodynamics. It's the theory of strong interaction. This is just for sake of discussion. Let's talk physics. It's not for the sake of this course, okay? But you might know that in QCD, the generating functional, well, let's suppose we are only interested for simplicity, not without loss of generality, just to show you what I'm talking about. We are interested only in computing observables of colorless operators. Why? Because colorful objects cannot be observed in QCD because of the phenomenon of quark confinement, right? So typically, and suppose that this colorless operator only coupled to quarks and not to gluons. Why? I mean, I don't want to do a course in QCD here. I just want to give you an example, okay? So maybe you have a couple of sources, or maybe I have a source. I will define what this source is in a moment. And then this is a QCD, so there will be fields for the quarks. There will be fields for the gluons. There will be the QCD Lagrangian that will couple psi bar, psi, and the gluon field. And for instance, there will be sources that will couple to operators that have the right quantum numbers. For instance, you have, in principle, you can build all the operators with all isospin quantum numbers you want, or spin quantum numbers you want, or charge quantum numbers you want, right? But you cannot build operators with quark quantum numbers. Now, clearly, all the observable you find at low energies would be combination of these operators here, right? Now, a big part of theory of strong interaction is based on the idea that you write the same partition function, but in terms of low energy effective fields. And what are the low energy effective fields? They are mesons. For instance, pions. Because, if you look at the spectrum of QCD, you have a ground state, and then the first excitation of QCD is the pion, which has 139 or 38 MeV, right mass. And then after the pion, you have all the mesons of the pion octet. Then you have to go to the eta prime. Then comes a proton, and blah, 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 blah. Suppose you're interested in the very soft dynamics, all you need is pion, and then basically you have an effective Hamiltonian with sources that couple to operators written in terms of pion degrees of freedom. And this equality is used to construct this effective theory, so that when you compute correlation function of this theory by differentiating with J, you have two equivalent forms, and therefore you can compute in the effective theory. So this is just a curiosity as far as this course goes, but I'm trying to say that the concept of generating functional is more extends further than it does in simply perturbation theory and statistical mechanics. Okay? Having said that, in the other lecture, last lecture, we began discussing the only case in which, well, it's not the only case. It's one of the only general case in which the generative function line can be evaluated exactly. And it's in the case of quadratic Hamiltonians. Now, quadratic Hamiltonians are trivial because the equations of motion are linear and therefore they obey superposition principle. Right? Now, if you have dynamics, and this is a quantum field theory, a linear equation obeying superposition principle means that when two waves will meet each other, they will not feel each other. They will cross it one on top of the other, like does almost completely. Okay? So in this sense, quadratic Hamiltonian theories are not most exciting. They don't contain much dynamics. So the idea would be you use them as the unperturbed state, and you think later, and this is something we will do, of treating corrections to this due to the non-harmonic behavior of the Hamiltonian, more higher order terms in the Hamiltonian, as small perturbation on top of this quadratic term. Okay, so what we will gonna work through is a path that leads to perturbation theory in which the unperturbed state is the quadratic Hamiltonian state. So if these were quantum fields, this would be a weakly interacting quantum field theory, because the quadratic Hamiltonian would correspond to a free quantum field theory. Okay? So I know that one of you who's not present today has not taken quantum field theory. Everybody else in this room has taken quantum field theory, for curiosity? Does anybody here who has not taken quantum field theory? Okay, so at least you know keywords wise what I'm talking about. Okay, very well. So let's make one step further. Let's do this integral. So let's begin. So what we want to do is to solve this problem here, which I will now write in the following way. Let's see if you agree with me. Where W is a local operator, and for instance, to be specific, we might have in mind the standard operator that enters in the quadratic term of Landau theory or in the free term of Klein-Gordon theory. Okay? We can call this R, or we can call it M. It doesn't matter. Statistical mechanics normally uses R. Quantum field theory uses M for obvious reasons. We don't care. Now, again, we are using this notation to denote a double integral. So this is just a notation of a bilinear. Now, if you remember, if this is local, locality means that Wx of y can be written as a delta of x of y times at most a differential operator let's call it, I don't know, small o at x. Okay, like in this case here. So this is a bilinear, but it's almost not a bilinear, because then if you have this structure, if you have a local operator, this bilinear is actually one sum. So in the following, rather than call it this O, we'll keep on calling it W, and we will assume the bilinear to be in this form, okay? So in the rest of this discussion, this will be this, okay? And then, of course, J dot dub phi is just a okay. So in the last lecture, we got this idea of completing the square. Remember, shifting variables, because if this integral is quadratic, well, I'm adding just a linear term. It still is a quadratic Hamiltonian, just shifted the origin by a little bit, right? So the idea would be to shift the origin in the field space, so to make this truly a Gaussian Hamiltonian, Gaussian integral. Okay, so how do? We do it in the following way. First of all, let's introduce the Green's functions of the W operator. So in other words, we have a W operator acting on delta x minus y, and this is delta of x minus y. I need to stop for 1 second. Okay, so
Professore, non la sentiamo più.
sorry. So what do? We shift variables, which means we take our fields and we add something. Okay, so we add a convolution. We have to add some constant, because otherwise we are not shifting, we are changing variable, right? So whatever we add here must not depend on phi. So we have two more ingredients. We have delta and j, right? So what I'm going to do here is to add a convolution of delta and j. And I will put an arbitrary constant alpha here. And alpha will be determined at the end of the calculation to eliminate the linear coupling. So this will be set to cancel out linear couplings to J. Okay? Okay, let's do that. So let's write our Hamiltonian. Our Hamiltonian is going to be dx phi w phi. Let me keep away dx, and then I will plus j w, and then we're going to change fields. Phi prime is equal to phi plus alpha delta J, right? Okay. First of all, we notice that the Jacobian of this transformation is simply 1, because shifting variable doesn't change the Jacobian, right? So let's do that. If I plug this back, I will get that H. So that means that basically D in D phi will go into D phi prime. The measure is left unchanged. So now everything that is left to look at is the Hamiltonian, the exponent. So let's look at the Hamiltonian. Let's look at the exponent. So let's call the exponent I, where I is H plus J phi. So let's look. Sorry. Let's call it, this was already contained in here. Sorry. So I have to call it J, H, because these both terms are inside H here. Let's not introduce more confusion than necessary. So let's look at the Hamiltonian now. The Hamiltonian is going to be phi prime minus alpha delta J W phi prime minus alpha delta J, correct? And then plus J sorry guys, this is J phi, of course, not J omega. It's the linear coupling to the field right here. There was a typo. Plus J phi prime minus alpha delta cross J. Okay, so all we need to do now is to expand this product. I will get phi prime or W phi prime. I will get negative alpha delta dot J dot W dot phi prime. I will get negative phi prime negative alpha phi prime W delta J, and I will get alpha squared delta J dot W dot delta J. If you get confused with all this notation, you can write your integrals explicitly. I'm just saving time here. Every time you see a dot, it's a convolution or an integral, okay? And then, of course, you have the last line. I'm going to get negative J phi prime, sorry, plus and negative alpha J delta J. So this is what the Hamiltonian gets transformed to after I go from phi to phi prime, right? Now, as you can see, this is equal to the original Hamiltonian. Let me call it H naught, written in terms of phi prime. That is this term here. So this is, let me be explicit, and I will write this as integral dx phi prime of x omega. And if I remember well, in the Hamiltonian here, where is the Hamiltonian? Yeah, please look at the screen. We have defined this to have a 1/2 here, right? So let me trace this back. Here, there is 1/2 missing. Here is 1/2 missing. So I have a 1/2 here. All of these terms have a half. And these two terms don't have a half, the last two terms. So let me go back and continue my writing. And I'm going to say this is, now I'm going to write this explicitly back and say this is dx phi prime of x w phi prime of x, which is the old theory now rewritten in terms of the phi prime. Okay. Now, let's look at these terms first. This term here. Okay, I call it 1. Here, I'm going to add terms here. But before I do that, let me go downstairs and look what each terms that enter here are. For instance, starting from this, let me use a different color just to highlight it. Oh, shoot. I will call this 1. So I go down here and I say 1. 1 is equal to negative half divided by 2. And then I have 2 integrals because I have a correlation functions. I have an integral in dx and an integral in dy because I have I have a propagator. So this will be phi prime of x w, and then I will have delta of x minus y jy, right? I've written explicitly this term. Now, since this is local, one of these convolution goes, and there are 2 integrals. You see 2 black spots here. That's why I have an integral in dx and dy. Now you begin to see why I've done the shifting that I've done, because what is this? Who tells me what happens when I evaluate this?
It's a delta.
It's a delta function. So this guy here becomes negative alpha minus 2, only the integral over x. And then I get phi prime of x, j of x. I'm beginning to build terms that can cancel out the term that I don't want. Okay? So there's another similar term here, which is slightly less easy, but ultimately you will see will lead the same results. And it's this term here, 2. Now the term 2 is very, very much looking like the same term, the previous term, but only the roles of the terms are interchanged. So I have integral in dx, integral in dy. So let's go back and look at it. It's delta of x minus y, j of y, because this comes from here, which is a function of x. This is a function of x, and this is a function of x, right? So I have delta of x minus y. This acts on x. And then, of course, I have my phi prime of x. Now, you can look at this as an inner product. So basically, this is delta phi w phi, right? Now, if this is Hermitian, as we are assuming because it's a Hamiltonian, then of course I can have it act on the other side. And the reason is that you can use part integration by part, essentially. To have, I mean, if it's a multiplicative terms, then of course you can move it wherever you want. If it has derivative, in order to be Hermitian, must have even number of derivatives. And when you have an even number of derivatives, you can act by part and act the derivative on the left and the right, because anytime you have a derivative, you change sign. But you have an even number of derivative, integration by part will not change the overall sign. You're familiar with these manipulations, right? So as a result of this, also this will give exactly the same result as before, because this will give me the delta function. And so we get exactly the same result as 1. So it means that basically 1 plus 2 will give me negative alpha integral dx delta of x minus y, sorry, j of x phi prime of x. Okay? Now it's clear what the value of alpha should be, because all I want to do is to cancel out this term that I called 3. Okay? So I will remove all linear terms. So if I set alpha to 1, then 1 plus 2 plus 3 equals 0. And what does the remaining part of the Hamiltonian? And the Hamiltonian will be 1/2 phi prime w phi prime. And now I'm left. I will not have this. I will not have this. And I will not have this. I'm left with these two states. And also I can everywhere see alpha. Now I can put 1. Now, for the same reason, if you look at the screen now, when W acts on this propagator will give me a delta function. So basically, these two terms are the same. They have a different coefficient. So as a result, this will be 1 negative integral dx integral dy j of x delta of x minus y j of y. So in the end, what I can say is that my partition function that I had started from will become e to the 1/2 j wj times the partition function of the remaining term. Now, you see, this guy here is nothing but a partition function of my theory with no source. So I can write the following. And this is a fundamental result of field theory. Now, it is quite clear that this is there, but there's no role. No role on observables, because any observable will come from functionally differentiation this with respect to the j and then divided by z, right? Because it will, this term would always cancel out. In endpoint correlation functions. You can leave it there, but it really doesn't matter. It's a number. But now with this expression, we can evaluate analytically any correlation function. Let's do the first two, and then you can play with the rest, okay? So let's suppose we want to evaluate this, the simplest correlation function. Well, all we need to do is to take limit for j going to 0. We will do this at the end. And take one functional derivative with respect to j with a negative. This will be of the e 1/2 delta j. I can take away z naught because ultimately I will divide by z of j with j going to naught. Right? So I can simplify these two terms. They don't play any role. Now, this will be limit. And then I will have 2 times. When I act on this, I can act here on here, right? I have 2 j's and 1 derivative. I will have 2 terms. So basically, I will get integral in the y delta of x minus y jy times 1/2 plus 1/2 integral dy j of y delta of y minus x. But I have to take the limit in which j goes to 0, right? And what is this limit?
Zero.
0. So there is no expectation value of a field in a quadratic theory by symmetry, if you want. In quantum field theory, you have a similar results because the quantum fields contains only either a creation or annihilation operator. Then you have vacuum, creation operation, vacuum, and this is bracketed to 0. That's an equivalent way of seeing the same thing. Okay? So you only have even powers. Green's function with an even number of legs in a quadratic theory by symmetry. Okay? Now let's do the next one. Phi of x, phi of y. Then this time you have to take two functional derivative, one to respect to j of x, one to respect to j of y. I am canceling the two negative signs. And then I will divide by, oh shoot, sorry. But I lost my, okay, I will divide by, I put a division by 1, but I put a limit over j going to 0 here. I'll put a square bracket, and then I will take also in front of it a 1 over zg of the square bracket. And of course, this will act on z of 0, e 1/2 j delta j. Just applying the definition, right? Nothing more, nothing less. As before, I can completely forget about this. And all I have to do is to take the second derivative with respect to the sources of this function out here, and then eventually set the sources to 0. So let's look at the, of course, let's do the first derivative first. So this is going to be derivative with respect to j of x. Sorry for being pedantic, but once in a lifetime, it's a matter of doing things all the way through. So I have the derivative of an exponent is the exponent itself times the derivative of the argument of the exponent. That is going to be delta of delta j of y of the integral in d z of, oh, I need some space here, j integral in dz, integral in dw, j of z, delta of z minus w, j of w, and then of course I have e to the 1/2 j delta j. Okay, just applying the rule of differentiation. Now I have a 1/2 here, of course. Now, as before, now this guy can act here, or it can act here. So I will have limit j going to 0 of d by dx, dj of x. I'm going to be very, very pedantic for once. 1/2 integral in dw delta of y minus w j of w. I've canceled this j and put a delta function instead. I have a second term. It's very similar, 1/2. Now I'm acting here. So I'm canceling the w, not the z. I would say dz. Delta, I get a j of z. I got a delta of z minus y. Now, it doesn't take much to understand that these two terms are actually one and the only, because the Green's function of my theory is invariant under interchange of x and y's, but I don't even need that. Remember, the Green's function is defined as the Green's function of my quadratic operator. And if you go to Fourier space, as we shall see, you can see that basically it must be j of y minus w must be equal to j of w minus y in a moment. We're going to see that, okay? So this is one and the only term, essentially. So how do I know? Okay, let me finish the expression, and then I have e to the 1/2 j w j, okay? Now, let me take a break and say nota, delta, let's solve for the x minus y. What is it? Well, let's be specific in the case in which w is our beloved Hamiltonian structure. It can be applied to any that has a derivative. Excuse me. Anything that has derivatives and constant terms, okay? So if you do this, then the idea is always the same. You go to Fourier space. This becomes p squared plus m squared times the Fourier transform in Fourier space. And this is the Fourier transform of a delta function. That is 2 pi to the 3. Well, actually, it really depends on how you define the delta functions, where you put the 2 pi. But let me suppose you put the 2 pi here. Okay? I actually prefer a definition, sorry, in which the Fourier transform of the delta is 1. But, you know, you can play around with the definition you want. The point is that up to a constant, this is 1 over p squared over m squared. And therefore, delta x minus y can be obtained by dp to the 3, 2 pi to the third, e to the negative I p dot x minus y divided by p squared plus m squared, right? Now, unlike the Klein-Gordon propagator you're used to, there's no need to put the I epsilon prescriptions because there's no singularity in the real axis here. You're used to having to put the I epsilon prescription, remember? Now, since the rest of the integral is even, obviously the Fourier transform is even under exchange of x and y's. And in fact, you know, in nuclear physics, you're familiar with this. Do you know what this is? What is the result of this integral? Have you seen this already? It has a very well known in nuclear physics. if it's not completely immediate to you, let me let you show that what happens if m goes to 0. This is the inverse of a sort of a Coulomb term, right? This would be the Coulomb term when m goes to 0, because the Fourier transform of the Coulomb is 1 over p squared, right? Now, this is like a Coulomb term with the mass of the photon. So it's a propagator of a massive particle. Have you ever heard of a Yukawa potential?
The Yukawa potential.
Exactly. So this is up to some 2 pi to the third, which I don't ever remember what it is. So let me put it in commas and you find the correct formula in the notes. This is going to be 1 over r e to the negative r, where r is x minus y. Hence the symmetry I was telling you before. So at least in 3D, this is easy. In 4D, you can calculate it, and it's a Bessel function of the second kind. And in 5D, you never need to do 5D. Why should you do 5D? But it's some kind of complicated function. Okay? The terms that are interesting is up to 4D, as far as I understand. And all of them have different expressions because they are field theory in different dimensions. The Green's functions, of course, have different structure. Okay? So now that we have the propagator, we can actually compute. First of all, we can go back here. We can go back here and eliminate, say, this one in favor of the 1/2 and leave only the e to the 1/2 j delta j term here. Now, what happens when I act with the second derivative? Well, now this time I have two options, because the second derivative can either act on the prefactor of the exponent, on this j here, or it can act of any of these two. Right? However, when this acts on this, let's say when you follow this path here, when you act on the exponent, you're going to drop an extra factor like this, right? And what happens when j goes to 0? This will go to 0. The only way you have to avoid getting a 0 is when the prefactor matches exactly the number, sorry, the number of derivatives that are here matches exactly the j's in the prefactor, right? Because basically all I'm saying that this is going to be delta of x minus y plus terms of order j or higher power of j. And these terms of order j will all cancel out in the limit j goes to 0. Do you follow me? So what we learned in this second exercise is that the 2-point correlation function is actually the propagator. Sorry, the Green's function of the quadratic, the inverse of the quadratic operator. Okay. Now, you should, this expression should resonate with you with this expression, right? That you might have seen in quantum field theory. Right? When you define the Feynman propagator of your Klein quantum field. The reason why you can do this is, and we're going to save one lecture to show, is that in fact you can represent quantum field theory as a path integral, and therefore everything that we say basically provide a derivation of standard quantum field theory results. Okay? Okay, now the same procedure can be generalized to any endpoint correlation functions. And what we're going to find is that typically any odd number of fields they are going to be zero because they are going to be order J in the end of the day, because I cannot kill all the J's in the prefactor by functional differentiation. Now, what happens to those with an even number of fields? Well, typically, I think you can convince by looking at the 4, 6 correlation function, and you immediately see how things work. But basically, if you have a, say, let's do a 4-point correlation function. When you act with the sources, you always you have 4 different functional derivatives over jy, jz, j omega, jx. And anytime you can act on the exponent or on the prefactor. When you act twice on the prefactor, you get a delta, right? So let's say I act with this functional derivative on the prefactor. Say I act with this on the exponent and with this of the prefactor. I will generate a delta of x minus y. Then necessarily with the remaining the functional derivative, I must do the same. I must act. If I act on the prefactor, there's no more j, and I get 0. If I act on the exponent, I will get 1j, and the second functional derivative must act on the prefactor. Otherwise, I will get something of order j. So when I act this on the exponent and this on the prefactor, I will get another z minus w. But of course, I can do all possible combination. I can also have a term in which I act with the first derivative on the exponent and with the derivative respect to x on the corresponding prefactor, and I will get the term delta x minus z. And I can act with the first derivative on the exponent and the second on the prefactor, leading to delta of y minus. So the act of having 2 derivatives, one acting on the exponent and the other the corresponding prefactor, is called a famous contraction. So the endpoint functions is the sum of all contractions leading to expression delta x minus y delta z minus w plus delta x minus z delta y minus w plus delta x minus w delta y minus z. Now the relative sign is always positive because we are dealing with objects that don't have fermionic character. If these were fermions, you would get alternating signs depending on the number of commutations. But this is the path integral with fermions. I leave it to Vanzo to enjoy. Okay. So graphically, what did we discover? That our 4-point correlation function, I could draw it in the following way. I have 4 points, x1. I now use, okay, let's do x, y, z, and w. And I graphically represent a 4-point correlation function in this way with a blob inside. That's a graphical way of representing G4 X, Y, Z, W. And if this is a quadratic theory, then this is going to be there's 4 combinations, and I'm going to represent this graphically. I'm going to represent graphically as a line between X and Y, the 2-point function between X and Y, the correlation function, which is also the Green's function. So I can write this as XY ZW plus XZ YW plus XW YZ. And here goes our first Feynman diagrams obtaining path integral representation. Questions? So by continuing this way, we can evaluate now arbitrary correlation functions. And once we have written this, I mean, these really are expressions we can evaluate. These are numbers. They look like graphs. But if I want to teach a computer to evaluate this, I will say in the 3-dimensional case, this is a Yukawa. I think I don't remember whether the Yukawa has a 2 pi to the 3rd numerator or denominator. Let me put it in the numerator for sake of definiteness. And this is x minus y e to the minus m x minus y times 2 pi to the 3rd z minus y w e to the m z minus w plus all the others. This is just this term, right? So eventually I have an analytic expression that I can write and get a number out of it. That means calculating the 2-point function, right? So going back, we motivated this phi to the 4th phi square theory as a paramagnetic theory, for instance. Well, if I'm true, if m is the inverse of the correlation length in the paramagnetic phase, I should be able, and if I can measure from, say, neutron scattering the correlation length in the paramagnetic phase, I should be able to compare this expression to experiment if I have a chunk of paramagnetic iron. You see? So this is really a way to compute things and ultimately match them. Okay, so here goes our discussion. here goes our discussion of the theory with quadratic interaction. And basically, if the theory is quadratic, you have a way of computing any number, any arbitrary correlation function, so you have completely solved the theory. So free theory is trivial, or paramagnetic theory with a simple quadratic Hamiltonian is trivial. Of course, physics starts when you have interactions. For instance, if this was really a quantum field theory, there's no way you can probe quantum field theory if you don't couple it to something, right? If you have some quantum excitations that doesn't interact with anything else in the world, you'll never be able to observe it, neither to observe any physical consequences of it. So you'll never know. In other words, we don't know if there is a pool of particles, I don't know, my name is Pietro, called the Pietrons in the world, if they have no mass and no other coupling with the four fundamental forces, because any measurement will never see them, and we will never be able to see anything. So if all in the world was just quadratic theory, there would be nothing to observe, nobody to observe. So in some sense, it's interesting, but it's useless as such. It's a little bit less useless if you talk about the statistical mechanics of it and paramagnetic. You may say, I'm interested in Hamiltonian describing finite correlation functions, and I can measure them, fine. Then you can get predictions out of it. But you would all agree that this is not particularly rich nor interesting. Action starts when you get coupling that are nonlinear, theories that are nonlinear, where superposition principle doesn't apply. And that's what we're going to start discussing next lecture. Okay? So here goes the first week in statistical field theory, so to say. And we will continue with perturbation theory next week and derive Feynman diagrams from path integral formulation. Bye bye.
Buon fine settimana.
Sì, va bene.